Hello friends, welcome to lecture series on matrix analysis with applications. Our today's lecture is based on inner product, what inner product is, and how we will see some important properties of inner product also. So, what is inner product? Let us see. So, let F be a field of real numbers or the field of complex numbers, and V be a vector space over F. An inner product on the vector space V is a function which is denoted by this from V cross V to F satisfying the following properties. So, these are the 4 properties which a inner product must hold for every x y z in V and for every alpha in field. So, what are these 4 properties? Let us see. The first property is inner product of x cross x is always greater than or equal to 0, and it is equal to 0 if and only if x is equal to 0. This is the first property. The second property is inner product of x and y is equal to inner product of y and x whole bar, where bar is a complex conjugate. The third one is inner product of x plus y comma z is same as inner product of x z plus inner product of y z. And the fourth property is inner product of alpha x comma y is same as alpha times inner product of x comma y, where alpha is any scalar in field. Okay. So, if you have a function which is defined like this from V cross V to F satisfying these 4 properties, then that product is called inner product. Okay. And that vector space defined in which this inner product is defined is called inner product space. Now, one important property which can be seen from the 4th property, you see, if you take inner product of x comma alpha y, so that will be equal to inner product of alpha y comma x whole bar by second property. So, this can be written as using this property, this can be written as alpha time inner product of y x whole bar, which is equals to alpha bar and the inner product of y comma x whole bar, and this is alpha bar, and the inner product, the complex conjugate of this from the second property is equals to inner product of x comma y. So, if this scalar is in the second with the second component, then it is alpha bar, and if it is the first component, then it is alpha. Now, let us discuss first few examples based on this. The first example is the dot product in Rn. If we define a dot product in Rn which is defined as this, then this is a inner product space, defines the inner product. Let us see how. You see, you are taking V as Rn and field as R, okay. And if you take U as A1, A2 up to An, and V as B1, B2 up to Bn, then the inner product of U and V is simply summation of Ai, Bi, I from 1 to n. Now, this can easily be shown. You see, the first property is inner product of U comma U. What is inner product of U comma U? It is summation I from 1 to n Ai into Ai, which is simply summation I from 1 to n Ai squares or A1 square plus A2 square up to An square, and that is always greater than or equal to 0. And this inner product is equal to 0 if and only if, you see, if it is equal to 0, this implies sum of Ai is equal to 0, and this implies Ai equal to 0 for all I, Ai equal to 0 for all I, okay. And this means U equal to 0, and of course, if U equal to 0, then this implies inner product of 0 comma 0 is of course 0 by this definition. So, the first property holds. Now, for second property, you can see inner product of U comma V. If you write, it is A1 B1 plus A2 B2 and so on up to A and Bn, This can be written as B1 A1 plus B2 A2 and so on up to Bn An. So, this is same as inner product of V comma U. Because we are talking in real space, I mean real field, it is a real vector space. So, bar it itself. Now, the third property is inner product of U comma V comma U plus V comma W is equals to, you can see if you take W as C1 C2 up to Cn, then this will be equals to summation I from 1 to n, it is Ai plus Bi times Ci by this definition, which is summation over I Ai Ci plus summation over I Bi Ci, and this is equal to inner product of U and W plus inner product of V and W. So, third property also holds. Now, the fourth property is inner product of alpha times U comma V is equals to, this is summation I from 1 to n. So, it is alpha times Ai Bi as you can already see, and this is equals to alpha times summation I from 1 to n Ai Bi, which is equal to alpha times inner product of U comma V. So, hence we have seen that all the four properties hold over this definition. When we define the inner product by this, all the four properties hold. So, this defines inner product, and the vector space over which this inner product is defined, we are calling that vector space as inner product space. So, there may be some other ways also to define the inner product over Rn. This is one of the way we are defining the inner product between U and V. Now, if you take Cn, I mean vector space as Cn over the complex field, then the inner product may be defined like this. Okay. This is again formed the inner product, this can easily be verified. You see, we are taking V as Cn and field as C. Okay. Now, inner product of U and V for any UV in Cn is defined like this, I from 1 to n, it is Ui is Vi is bar, conjugate of this. We are taking U as U1 U2 up to Un and V as V1 V2 up to Vn. Okay. So, the first property is that inner product of U comma U, it is equals to summation over I Ui into Ui bar, which is summation over I mod of Ui squares. This means mod of U1 square plus mod of U2 square and so on up to mod of Un square. So, this is always greater or equal to 0 for all U. Now, if this is equal to 0, this implies mod of U1 square plus and so on mod of Un is equal to 0, and this implies mod of Un is equal to 0 for all I, and this implies Ui equal to 0 for all I, and that means U equal to 0. Now, if U equal to 0, of course, inner product of 0 comma 0 is 0. So, the first property holds. Now, for second property, inner product of U comma V, if you take is summation I from 1 to n Ui Vi bar, which can be written as summation I from 1 to n Vi Ui bar whole bar. Okay. And this is inner product of V comma U whole bar. So, second property also holds. Now, the third property is inner product of U plus V comma W, that is equals to summation Ui plus Vi into Wi bar over I, where we are taking W as W1 up to Wn. So, this is summation over I Ui Wi bar plus summation over I Vi Wi bar, and this is inner product of U and W plus inner product of V and W. The fourth property is inner product of alpha U and W is equals to summation over I alpha Ui into Wi bar which is equals to alpha times summation over I ui wi bar, which is alpha times inner product of u and w. So, we have shown all the 4 properties over this definition. That means, this defines an inner product over the complex over Cn over the complex field. Now, similarly, we can go for the third problem, that if we define a vector space, if we take a vector space of all real continuous functions on the interval, on the closed interval a to b, and we defined as the product as integral a to b f t g t dt, then this defines an inner product. Very easy to show, because you can simply see that if you take f and f, inner product of f and f, then it is simply f square from a to b, which is always greater than or equal to 0 for every f. And if f inner product of f and f is equal to 0, that means integral a to b f square equal to 0, and that is true only when f equal to 0. So, the first property holds. Now, when you take inner product of f and g, or g or f, both are same, because f t into g t is same as g t into f t. Now, inner product of f plus g comma h, if you take f plus g into h, so that property, the third property, can be directly obtained. And alpha times f comma g is, you can simply take alpha outside the integration, and we can get the fourth property also. So, this definition define inner product on the vector space C of closed interval a b. Now, if we take this example, we considered all the matrices, all the real matrices of order m cross n over the real field, and this defines the inner product. How it is defined inner product, let us see. So, here we are taking vector space as all matrices of order m cross, real matrix of order m cross n, and field as real, okay. And inner product between matrices A and B we are defined as trace of B transpose A, which is simply summation over I, summation over j, Aij, Bij. Now, the first property is that inner product of A and A. Inner product of A and A means trace of A transpose A, which means summation over I, summation over j, Aij whole square, okay. Then that is always greater or equal to 0, of course, because it is sum of non-negative quantities, okay. Now, inner product of A comma A is equal to 0 implies summation I, summation j, Aij whole square equal to 0, and that is true only when Aij equal to 0 for all I and j, and that means matrix A itself is 0, okay. And again, if matrix A is 0, the definition trivially holds, because it is inner product of 0 and 0, that means trace of 0 transpose 0, which is of course 0. So, the first property holds. Now, if we take the second property, that is A and B, which is same as trace of B transpose A, which is given by summation I, summation j, Aij, Bij. If this can be written as summation over I, summation over j, Bij, Aij. So, we can easily write it trace of A transpose B, which is inner product of B and A, okay. Now, a third property is inner product of A plus B and C, which is same as trace of C transpose A plus B by the definition, which is trace of C transpose A plus C transpose B, and this can be written as by the property of trace, that trace of C transpose A plus trace of C transpose B, which is inner product of C and with inner product of A and C, sorry, A and C, and the plus inner product of B and C. So, third property also holds. Now, for the last property, it is trace of inner product of alpha A comma B is equals to trace of B transpose alpha A, which can be written as summation over I, summation over j, here we will replace Aij by alpha times Aij. So, alpha times Aij, because all you are multiplying A with alpha. Okay. So, it is Bij, this can be written as alpha times summation over I summation over j Aij Bij, and this will be alpha times trace of B transpose A, or alpha times inner product of A and B. So, hence we can say that all the 4 properties holds over this definition, that means this defines an inner product for this vector space over this field. So, these are the few examples of inner product. Now, when we can say that two vectors are orthogonal. So, two vectors are said to be orthogonal if the inner product of between them is 0, then we say that u and v are orthogonal. Now, let us see this problem. Consider vectors u equal to this v and w. The first problem is u orthogonal to v and w? So, you see here we are defining inner product as a standard inner product, that means a dot product. If nothing is given, that means we are taking the inner product as the dot product of the two vectors. So, what is dot product of u and v? It is 1 plus 2 is 3 minus 3 is 0, that means u is orthogonal to v, it is clear. Now, is u is orthogonal to w also? So, let us see, 1 into 1 is 1, 1 minus 4 minus 4, 1 minus 4 is minus 3 plus 3 is 0. So, yes, it is orthogonal to w also. So, the first part, the answer of the first part is yes. Okay. Now, is v orthogonal to w? So, to see that v is orthogonal to w, try to find out the inner product of v and w, and if it is equal to 0, that means v is orthogonal to w. So, see here, 1 into 1 is 1, 2 into minus 4 is minus 8, and 3 into minus 3 is minus 9, it is not equal to 0 clearly. So, v is not orthogonal to w. Now, find a non-zero vector w that is orthogonal to u1 and also u2. So, what is u1 and what is u2? Here u1 is, it is 1 2 1 and u2 is, it is 2 5 4. So, we have to find a non-zero vector w which is orthogonal to, w is orthogonal to u1 and w is orthogonal to u2 also. That means the inner product of w and u1 and inner product of w and u2 is equal to 0. So, a vector which is orthogonal to these two vector is simply the cross product of these two. Okay. So, simply find the cross product of these two, that is will be a w which is orthogonal to these two vectors. Okay. So, how to find w? So, w will be simply you find the cross product of these two. Cross product of these two will be I j k, it is 1 2 1 2 5 4. So, it is I cap times 8 minus 5 is 3 minus j cap time it is 4 minus 2 is 2 plus k cap times it is 1. So, we can say that w is simply 3 minus 2 1. You can check also, you see 3 into, if you take the inner product of w and u1. So, what is inner product? It is 3 minus 4 plus 1 which is 0. Inner product of w and u2 is it is 6 minus 10 plus 4 which is again 0. Of course, it will be, because it is the cross product of these two vectors and hence w will be orthogonal to these two vectors. Or the other way out is, in fact any alpha times this vector 3 minus 2 1 will be orthogonal to u1 and u2 both. Now, how we define orthogonal complements? Let S be a subset of an inner product space V. The orthogonal complement of S denoted by S perpendicular, okay, consists of all those vectors in V that are orthogonal to every vector of U belongs to S. U is a subset of inner product space V. So, this is orthogonal complement of S which is given by all those V in V such that inner product of V and U is 0 for every U in S. In particular, for a given vector u belongs to V, we have orthogonal complement of u as or that V which is orthogonal to u, okay, collection of all those V which is orthogonal to u. Now, the first property of this orthogonal complement is that it is a subspace of V. So, how we define orthogonal complement? Orthogonal complement is basically a subset of vector space V, which is defined as all those V in V such that inner product of V and U is equal to 0 for all U in S. S is a subset of V. Now, in order to show that this is a subspace of this vector space V, let V1, V2 in S orthogonal complement and alpha belongs to field. And we have to show that alpha V1 plus V2 also belongs to S complement, this to prove. Okay. To show that it is a subspace, we have to show that this also belongs to orthogonal complement of S. So, how we will show this? So, let us try to find out the inner product of this with any u in S, for any u in S. Now, this is equals to, by the definition of inner product, this is this u plus V2 comma u. Again, this is alpha times inner product of V1 u plus inner product of V2 u. Now, since V1 and V2 are in orthogonal complement of S, so this is 0 and this is 0 for any u. So, this is equal to 0. So, we have shown that alpha V1 plus V2 belongs to orthogonal complement of S, and that means orthogonal complement of S is a subspace of S of V. Okay. Now, we have few geometric interpretations of complement, orthogonal complement. Suppose that u is a non-zero vector in R3, okay. Then orthogonal complement of a vector u is a plane in R3 passing through origin and is perpendicular to the vector u. You see, what is an orthogonal complement? Orthogonal complement of element are all those V in V such that orthogonal complement inner product of V and U is equal to 0, So, how we can see geometrically? Geometrically, it is simply all the planes, it is something like plane. You see, we have to find out V, all the planes which are passing through origin, because it is equal to 0, okay, and perpendicular to U. It is very clear from the definition itself. Now let the second one is, let W be a solution of a space of an M cross n homogeneous system of equations Ax equal to 0. Suppose for this equation, for this system of equations, the solution space is W, okay, where A is of matrix Aij and X is a column vector Xi. Then each solution W, which is given by x1, x2 up to xn, is orthogonal to each row of A, and hence W, the kernel space of the linear mapping A from Rn to Rm, is the orthogonal complement of the row space of A. You see, here we have a matrix of order m cross n, and X is a column vector of order n cross 1. Okay. You see, here we are having A into X. A is a matrix A11, A12 and so on up to A1n. Similarly, AN1, AN2 and AM1, AM2, AMn. And here it is x1, x2 up to xn equal to, it is 0, 0, 0. What does it mean? This means that when you multiply this row with this column, it is equal to 0. The second row with this column is equal to 0. The third row with this column is equal to 0. So, what does it mean? This means that that every row is orthogonal to this. Okay, that's what it is. Here that each solution is orthogonal to each row, because the inner product of row and the xi is 0. Okay. So, each solution is orthogonal to each row and hence W is the orthogonal complement of the row space of A. So, this W which is solution space of this is simply the orthogonal complement of row space of A. Row space is a space generated by the rows of A. So, this is all about inner product space. So, in this lecture we have seen that what inner product space is and what are the properties of inner product. We have also seen that if a set is known to you, then how we can find out orthogonal complement of that S. Thank you.